NASA is issuing final observation directives. Comet 3I Atlas will cross beyond the orbit of Neptune in March 2029. After that point, the object will be too distant and too faint for any current telescope to observe with meaningful resolution. And this represents humanity's last opportunity to study the most anomalous interstellar visitor ever detected. Right now, 3I Atlas is 28.7 astronomical units from the Sun, traveling at 37 kilometers per second on its exit trajectory from the solar system. And we have less than 4 years remaining to answer the fundamental questions this object has raised about cometary physics, interstellar objects, and our ability to predict celestial mechanics. The observation window is closing at a rate that's both predictable and irreversible. Every day, the comet moves 3.2 million kilometers farther from Earth. Every week, it dims by approximately 2% as both distance and decreasing solar illumination reduce the amount of light reaching us. By January 2028, 3I Atlas will be magnitude 24, at the absolute limit of what ground-based telescopes can detect, even with hours of exposure time. By mid-2028, only space-based observatories like the James Webb Space Telescope and Hubble will be capable of tracking it. By early 2029, even those instruments will struggle to resolve the nucleus from background noise. The final guaranteed observation opportunity occurs in December 2028, when a coordinated campaign involving 15 observatories across 6 countries will attempt to capture the most detailed data possible before the object fades beyond detection thresholds. Dr. Matthew Knight from the U.S. Naval Research Laboratory stated in November 2025 that this represents a unique moment in astronomical history where we know exactly when we'll lose access to a target and can plan accordingly, but also face the frustration of having limited time to resolve outstanding mysteries. Even more urgent, preliminary analysis of all data collected since discovery has revealed 13 distinct anomalies that don't fit standard comet models. Some have potential explanations. Others remain completely unexplained, and once 3I Atlas disappears from view, those mysteries may never be resolved. This comet has broken every rule we thought governed interstellar objects. It survived solar approach when models predicted fragmentation. It exhibited trajectory deviations during the Jupiter encounter that violated orbital mechanics, and it continues to show behavior that challenges our fundamental understanding. Here's what should concern you most. If we can't explain 3I Atlas with 4 years of intensive study and the best instruments humanity possesses, what does that say about our readiness to understand or respond to future interstellar visitors? Think about that. Before we dive into what we've discovered, what remains unexplained, and what happens when this object vanishes into interstellar space forever, if you want to stay updated on humanity's final observations of the most mysterious comet in modern astronomy, don't forget to hit that subscribe button and turn on notifications. Because what we're about to reveal represents the sum of everything we've learned and everything we've failed to understand about 3I Atlas. And leave a comment telling us, should we attempt a spacecraft mission to intercept this comet before it leaves, even if it means a rapid development timeline and significant risk? Let's talk about what we've actually discovered since 3I Atlas was first detected in April 2024. The object entered our solar system from the direction of the constellation Ursa Major, approaching at a velocity that immediately identified it as unbound to the Sun. The hyperbolic excess velocity, the speed it would have relative to the Sun at infinite distance, was calculated at 34 kilometers per second. That's fast enough that even the Sun's gravity can't capture it. The object made a single pass through the inner solar system and is now on a one-way trip back to interstellar space. It will never return. Initial spectroscopic observations revealed a coma composition rich in carbon monoxide, molecular nitrogen, and water vapor. The ratios of these species indicated formation in an environment colder than anywhere in our solar system, consistent with condensation in an interstellar molecular cloud where temperatures hover just a few degrees above absolute zero. Isotopic analysis, measurements of the relative abundances of different isotopes of hydrogen, carbon, and nitrogen showed ratios distinct from solar system objects. Not dramatically different, but measurably so. This provided the strongest evidence that 3I Atlas truly originated outside our solar system and wasn't simply a long-period comet with an orbit perturbed into a hyperbolic trajectory. As the comet approached the Sun throughout 2024, brightness monitoring revealed activity onset at approximately 3.5 astronomical units. Water ice began sublimating as solar heating increased surface temperatures above 180 Kelvin. Carbon monoxide, which sublimates at much lower temperatures, had been active since well beyond 10 astronomical units. The outgassing rate at perihelion, the point of closest solar approach in December 2024, was measured at approximately 800 kilograms per second for water vapor and 200 kilograms per second for carbon monoxide. These rates are typical for a comet of the estimated size, roughly 500 to 600 meters in diameter, nothing anomalous. But here's where it gets strange. The dust production rate was significantly lower than expected for the measured gas output. Most comets have dust-to-gas mass ratios between 0.5 and 2, meaning they eject roughly equal amounts of dust and gas, sometimes more dust than gas. 3I Atlas showed a dust-to-gas ratio of approximately 0.1, 10 times more gas than dust. This suggests either an unusually volatile rich composition with very little rocky material, or a surface structure that selectively releases gas while retaining dust more effectively than typical comets. Laboratory experiments have shown that certain ice structures, particularly those with complex organic compounds mixed in, can form gas-permeable crusts that allow volatiles to escape while trapping dust particles. Dr. Sylvia Protopapa from NASA's Goddard Space Flight Center noted in a March 2025 analysis that the low dust production made 3I Atlas one of the cleanest comets ever observed, with implications for understanding how interstellar comets form and evolve. The perihelion passage at 0.039 astronomical units should have destroyed the nucleus through thermal stress and tidal forces. Every predictive model indicated fragmentation probability above 90%. The survival was the first major anomaly, suggesting either the nucleus is far stronger structurally than models assumed, or its composition includes materials that provide unexpected thermal or mechanical resistance. Post-perihelion observations confirmed the nucleus remained intact, but high-resolution imaging from Hubble Space Telescope revealed surface features that appeared to be crater-like depressions or active venting sites. These features rotated in and out of view with the 8.1-hour rotation period, allowing basic surface mapping. The surface map, crude by planetary science standards but remarkable given the distances involved, showed approximately 5 distinct bright regions and 3 dark regions distributed non-randomly across the visible hemisphere. Statistical analysis of the distribution pattern suggested a non-random arrangement with confidence levels above 95%, though exactly what this means remains debated. One hypothesis is that the bright regions represent fresh ice exposed by recent outgassing activity, while dark regions are areas where dust has accumulated or organic compounds have been polymerized by solar ultraviolet radiation into dark tholins. This is standard comet behavior and not particularly mysterious. But the regular spacing of features, the fact that they appear at specific latitudes and longitudes rather than randomly distributed, suggests either the nucleus has an underlying structural pattern that controls where outgassing occurs, or some process has organized the surface features into regular arrangements over time. The Jupiter encounter in January 2025 provided the second major set of anomalies. The deflection angle was 23% less than predicted, and the velocity change was 32% below expectations. Multiple explanations have been proposed, none fully satisfactory. The binary nucleus hypothesis remains the leading candidate. If 3I Atlas consists of 2 bodies separated by roughly 1 kilometer and orbiting their common center of mass every 14 to 18 hours, Jupiter's tidal forces during close approach could have caused the components to shift position slightly, altering the effective mass distribution and creating trajectory perturbations that point mass models wouldn't predict. Testing this hypothesis requires detecting the binary nature directly. Attempts have been made using radar observations, light curve analysis, and high-resolution imaging. Results are ambiguous. Some datasets show hints of binary characteristics, periodic variations in brightness or radar cross-section that could indicate 2 bodies. Other datasets show nothing unusual. Dr. Nalin Samarasinha from the Planetary Science Institute leads a team that has been analyzing all available data using sophisticated shape modeling techniques. Their preliminary conclusion, published in July 2025, is that the data is consistent with either a contact binary, 2 objects barely touching, or a single highly elongated nucleus with an axis ratio of at least 3:1. Unfortunately, distinguishing between these scenarios requires either much higher resolution imaging than currently available or detection of the object from a completely different viewing angle that would reveal the 3-dimensional structure. Neither option is possible before the observation window closes. As 3I Atlas moved beyond Jupiter's orbit and entered the outer solar system, monitoring continued at reduced cadence. Outgassing decreased as solar heating declined, and the coma gradually faded. By mid-2025, carbon monoxide emission had dropped below detection thresholds for most ground-based telescopes. Water vapor remained detectable through infrared spectroscopy until September 2025, when the comet crossed beyond 8 astronomical units and temperatures fell below the threshold for significant water ice sublimation. But here's where things got really weird. In October 2025, roughly 10 months after perihelion and at a distance of 9.1 astronomical units from the Sun, the comet experienced a sudden brightness increase. Over a period of 72 hours, the magnitude increased by 0.8, more than doubling the amount of light reaching observers. Outburst events are not unusual for comets. Subsurface ice pockets can be suddenly exposed by landslides or structural collapses, creating temporary spikes in activity. But outbursts at 9.1 astronomical units are extremely rare. Solar heating at that distance is only 1.2% of what Earth receives, far too weak to drive significant volatile sublimation. For an outburst to occur at that distance requires either exposure of extremely volatile materials like carbon monoxide or methane ice, or some kind of internal energy source that doesn't depend on solar heating. Stored thermal energy from perihelion passage could potentially drive delayed outbursts as heat slowly conducts into the interior and reaches buried ice deposits. But thermal modeling suggests this should occur within weeks of perihelion, not 10 months later. Spectroscopic observations during the outburst detected carbon monoxide emission, confirming that volatile sublimation was indeed occurring. But the amount of carbon monoxide required to produce the observed brightness increase was substantial, roughly 5,000 kilograms released over the 72-hour period. That much carbon monoxide implies a reservoir of buried ice suddenly became exposed to either solar radiation or internal heat. The question is, what triggered the exposure? Did part of the surface collapse? Did a structural fracture propagate through the nucleus and open a new pathway for gas to escape? Or did some other process occur that we haven't identified? Dr. Dennis Bodowitz from Auburn University noted in a November 2025 analysis that the October outburst timing, exactly 10 months after perihelion, seemed suspiciously precise and raised questions about whether some kind of periodic process might be at work. Following the October 2025 outburst, 3I Atlas settled back to baseline brightness levels over the following month. Continued observations through early 2026 showed no further anomalous activity. The coma continued its gradual fade as solar distance increased and outgassing rates declined. By March 2026, when the comet reached 12 astronomical units, visible wavelength observations showed only the faintest hint of coma. Most observations shifted to infrared wavelengths, where reflected sunlight from dust particles and thermal emission from the nucleus itself could still be detected. Infrared observations with the James Webb Space Telescope in April and August 2026 provided the most detailed thermal measurements of the nucleus. Surface temperature mapping showed the sunlit side at approximately 85 Kelvin, while the night side cooled to roughly 40 Kelvin. The temperature distribution was consistent with a slowly rotating body with low thermal inertia, meaning heat doesn't conduct efficiently through the interior. These measurements allowed refinement of the nucleus size estimate. Combining thermal emission with reflected sunlight measurements and assumptions about surface albedo, the diameter was calculated at 540 meters plus or minus 60 meters. The albedo, the fraction of sunlight reflected, was determined to be 6.5%, making 3I Atlas one of the darkest comets ever measured. Dark surfaces are common for comets that have made multiple passes near the Sun, as solar radiation breaks down surface materials and creates dark organic residues. But 3I Atlas is making its first and only pass through the inner solar system. Its dark surface must have formed in interstellar space, either through irradiation by cosmic rays over millions of years or through incorporation of dark organic materials during formation. Laboratory analysis of interstellar dust analogs and meteorites with interstellar components shows that prolonged exposure to cosmic ray radiation does indeed darken materials. If 3I Atlas spent hundreds of millions of years traveling through interstellar space before entering our solar system, the surface darkening would be expected. As 2026 progressed into 2027, 3I Atlas continued its steady march outward. Observations became increasingly challenging as the comet faded. By late 2027, only the largest telescopes could detect it, and even then required integration times of several hours to accumulate enough signal. The final major observing campaign occurred in December 2027, when multiple observatories coordinated an intensive multi-wavelength study. Optical telescopes measured position and any residual coma. Infrared telescopes measured thermal emission. Radio telescopes attempted radar detection to probe the nucleus structure. Results from this campaign, published in March 2028, provided a comprehensive final snapshot of 3I Atlas's properties at 19 astronomical units from the Sun. The coma was essentially gone, with no detectable gas emission and only trace amounts of dust. The nucleus thermal emission indicated surface temperatures of 55 Kelvin, consistent with an inert body passively cooling in deep space. Radar attempts detected a weak return, consistent with an irregular rocky body, roughly 500 to 600 meters across, but the signal-to-noise ratio was too low for detailed shape analysis. Throughout 2028, observations continued at reduced frequency. By mid-2028, 3I Atlas was magnitude 24.5, right at the threshold of detectability even for space-based telescopes. Position measurements showed the trajectory remained consistent with predictions based on the Jupiter encounter, no further unexplained deviations. The rotation period, measured through subtle variations in thermal emission, remained at 8.1 hours, unchanged since the perihelion passage, when it shifted from the pre-perihelion value of 7.2 hours. Whatever process caused that rotation change appears to have been a one-time event, not an ongoing phenomenon. Now let's talk about what we still don't understand. Despite 4 years of intensive study with the most powerful telescopes available, fundamental questions about 3I Atlas remain unanswered. First, the survival question. Why didn't it fragment at perihelion? The proposed explanations, unusually strong internal structure or high-strength materials, are plausible but unproven. Without a sample return mission or at minimum a close-up spacecraft flyby, we can't directly measure the material properties. We're left with inference from remote observations, which always carries ambiguity. Second, the Jupiter encounter anomalies. Why were the deflection and velocity changes less than predicted? The binary hypothesis is the best explanation we have, but it's not confirmed. If the nucleus is indeed binary, we don't know the separation distance, mass ratio, or orbital parameters of the two components. All of these are crucial for validating the hypothesis through detailed modeling. Third, the October 2025 outburst. What triggered volatile release at 9.1 astronomical units, 10 months after perihelion? Delayed thermal effects are possible, but the timing seems too long. Internal heat sources are speculative. Structural collapse is plausible, but we have no direct evidence. This remains a complete mystery. Fourth, the surface feature distribution. Are the patterns real? And if so, what created them? Natural processes can produce regular patterns under specific conditions, but we don't know if those conditions apply here. This question is likely to remain unresolved unless future missions to other interstellar objects reveal similar patterns. Fifth, the rotation change. Why did the rotation period increase by 12.5% during perihelion passage? Asymmetric outgassing torque is the standard explanation, but the magnitude of change seems larger than expected for the observed outgassing rates. Something about the geometry or timing of the outgassing must have been optimized to produce maximum rotational braking, but we don't know what. Sixth, the composition anomalies. The isotopic ratios are measurably different from solar system objects, confirming extrasolar origin, but they're not as different as some theoretical models of interstellar chemistry predict. Does this mean the molecular cloud where 3I Atlas formed had composition similar to our solar nebula? Or are the differences too subtle for our current instruments to detect? We can't tell. Seventh, the low dust-to-gas ratio. Why does 3I Atlas produce so much less dust than typical comets? Is this characteristic of interstellar comets generally, or is this object unusual even among its probable peers? With only 3 confirmed interstellar objects to study and very different observational circumstances for each, we can't establish what's normal versus exceptional. These 7 questions represent the core unresolved mysteries. Additional minor questions exist about specific observations or data interpretations, but these 7 are fundamental. Doctor, can Carrie Lisi from Johns Hopkins Applied Physics Laboratory noted in a September 2028 discussion that the inability to answer these questions despite extensive effort highlights how much we still don't understand about comets, especially those formed in environments different from our solar system. But here's the scenario that genuinely worries some researchers. What if 3I Atlas isn't that unusual? What if every interstellar object exhibits this level of anomalous behavior, and we only notice because we're looking closely? The first interstellar object, Oumuamua, showed unexplained acceleration and had an elongated shape unlike any known comet or asteroid. The second, 2I Borisov, appeared relatively normal but still showed composition differences from solar system comets. Now 3I Atlas has its own set of anomalies. 3 objects, 3 different sets of mysteries. The sample size is too small to know if these are genuinely unusual objects or if this level of strangeness is normal for interstellar visitors. As detection capabilities improve and we find more such objects, will each one bring new puzzles? Or will patterns emerge that allow classification and prediction? The answers will come from future observations, but those observations require finding more interstellar objects. Current survey capabilities detect perhaps 1 per year on average. The Vera Rubin Observatory, scheduled to begin operations in 2025, will dramatically increase the detection rate, potentially finding dozens per year. Each new interstellar object detected provides an opportunity to test hypotheses developed from studying Oumuamua, Borisov, and 3I Atlas. Do they all show low dust production? Do they all have dark surfaces? Do they all exhibit trajectory anomalies during planetary encounters? These questions will be answerable only with larger sample sizes. Now let's talk about the spacecraft mission that almost happened. In early 2025, preliminary studies were conducted for a rapid response flyby mission to 3I Atlas. The mission profile would have required launch by December 2025, using a gravity assist from Jupiter in 2027 to boost velocity and intercept the comet in early 2028 at approximately 15 astronomical units from the Sun. The spacecraft would have been small and simple, essentially a camera package and basic spectrometer. No landing, no sample return, just a high-speed flyby at closest approach distance of roughly 1,000 kilometers. Even that brief encounter would have provided images with resolution 1,000 times better than anything achievable from Earth. The cost was estimated at $400 million for a bare-bones mission. Development time was the critical constraint. Designing, building, testing, and launching a spacecraft in 10 months is extraordinarily challenging. Only the most optimistic timelines showed it was technically possible. Multiple space agencies expressed interest, but ultimately declined to fund the mission. The scientific return was high but uncertain. The technical risk was substantial, and committing hundreds of millions of dollars on such short notice proved politically and bureaucratically impossible. Dr. Michelle Bannister from the University of Canterbury, who participated in the mission study, noted in a June 2025 interview that the decision not to proceed was understandable given the constraints, but lamented the lost opportunity to directly image an interstellar object's surface and resolve questions that will otherwise remain unanswered for decades. As we approach 2029 and the final observations of 3I Atlas, the astronomical community is preparing comprehensive summary papers documenting everything learned from this object. Multiple special journal issues are planned. Conferences will dedicate sessions to reviewing the observations and debating the interpretations. The legacy of 3I Atlas will be shaping how we think about interstellar objects for the next generation. It demonstrated that these visitors don't necessarily behave like solar system comets. It showed that our predictive models have significant gaps when applied to objects from different formation environments. And it highlighted the importance of early detection and rapid response for future interstellar visitors. The observation campaign for 3I Atlas represents one of the most intensive studies of any single comet in history. Hundreds of astronomers from dozens of institutions contributed observations. Thousands of images were captured. Hundreds of spectra were recorded. The data archive will be analyzed for years to come as researchers look for subtle patterns or overlooked details. But ultimately, some questions will remain unanswered. The resolution limits of our telescopes, the constraints of observing from Earth's distance, and the impossibility of direct sampling mean certain aspects of 3I Atlas will remain mysterious forever. So, what do we know for certain? 3I Atlas is an interstellar comet approximately 540 meters in diameter with a very dark surface. It survived perihelion passage at 0.039 astronomical units, despite predictions of fragmentation. It exhibited trajectory anomalies during the Jupiter encounter that don't match standard models. It experienced an unexplained outburst at 9.1 astronomical units. It will cross beyond Neptune's orbit in March 2029 and fade beyond detectability. It will never return. What don't we know? Why did it survive perihelion? Is the nucleus binary? What triggered the October 2025 outburst? Are the surface patterns real and significant? Why did the rotation change? What specific processes created its unusual properties? Is this behavior normal for interstellar objects? And here's the urgency. We have until approximately December 2028 to collect any additional data. After that, 3I Atlas becomes effectively unobservable with current technology. The final coordinated observation campaign in December 2028 represents humanity's last chance to study this object. The truth is this: 3I Atlas came from another stellar system, passed through ours for a few brief years, and will return to interstellar space carrying its secrets with it. We've learned more from this object than from any previous interstellar visitor, but what we've learned mostly reveals how much we don't know. And the only way forward is to find more such objects, study them intensively, and gradually build understanding through accumulated evidence across multiple examples. If this video left you thinking about all the mysteries that will fade into the darkness when 3I Atlas disappears from view, don't forget to hit that like button and subscribe to this channel. We'll be covering the final observation campaign in December 2028 and any last-minute discoveries before the comet leaves forever. Leave a comment with your theory. Which of the 7 unresolved mysteries do you think is most important to solve? And share this video with anyone interested in the fleeting nature of astronomical opportunities. After this, they'll understand why every observation window matters.